We discuss in this video about modeling with discrete-time Markov chains with a special focus on Markov chains as transition systems. Discrete-time Markov chains are discrete stochastic processes, meaning that the state space is discrete. And they also satisfy the so-called Markov property. The next state is only dependent on the present state and not on any of the past states. In other words, you can also say that this process has no memory. So formally, a discrete-time Markov chain is a sequence of random variables x1, x2, and so on, taking values in some set S, such that the probability that in the next state we have value x, given the whole past of the process, is exactly the probability that we have in the next state x, given that in the current state we have xn. So this is another formal mathematical way of writing this property that the transition depends only on the current state and not on any of the past states. This probability of having in the next state x, given that in the current state we have xn, is called the one-step transition probability from state xn to state x. And the set where we have the values in is called the state space of the chain. The Markov chain can be described by a labeled directed graph with the elements of S as the vertices and the transition probabilities as the labels of the edges between the states. Note that we are talking about discrete time and discrete state space. We will only consider in this course time homogeneous Markov chains, meaning that the transition probability matrix doesn't change in time. All of these mean that a Markov chain is governed by a single matrix that dictates each transition of the chain from one state to another. We denote that matrix as P, and its entry on row R and column S simply tells us what's the probability that the model will go in one step from state R to state S. P is also called a stochastic matrix, which means that it has quadratic cardinality. P of Rs is in between 0 and 1 for all states R and S, and the sum of these probabilities Rs, sum for all S's, it has to be 1, because from state R we will go somewhere, so this sum has to be 1. It's also easy to see that the nth power of matrix P is also a stochastic matrix for any n greater than or equal to 1, and we will return to this point in a short while. There is also another useful point of view, seeing a Markov chain as a computing machinery. Technically, this is called a transition system. It means that a Markov chain is really a computing device that has a current state and a decision to make to jump to another, possibly the same state. The jumps are dictated each time by chance according to the probability matrix P. Depending on the current state, the decision probabilities may be different. In other words, all in all, a probabilistic machine. Here is another interesting thing about the transition probability matrix P of a Markov chain. As we saw, it describes the probability of single jumps, but in fact it tells much more than that. Here is a useful question to answer. What's the probability of jumping from a state Q to a state S in exactly 2 steps, or in 5 steps, or in general in n steps? And here is how to reason about this when n is larger than 1. So I need to go from Q to S in exactly n steps. So let's make the first step from Q to some state R. Now, state R can be any state of the model, and the jump from Q to R is dictated by matrix P. And then I will make a transition in n-1 steps from R to S. We can formalize this in the following way. Let's denote by Pn the matrix describing the probabilities of transitions in n steps. And obviously in one step we already have and P1 is exactly P. As we discussed, the probability of going in exactly n steps from some state q to some state s is going to be something like this. First I need to go in one step from q to some state r, and then in n-1 steps from r to s. And since r can be any of the states of the Markov chain, I will have to sum up among r being anywhere in the set S. And obviously this means that Pn is equal to P1 times Pn minus 1. And this is because P1 is P, so P times Pn minus 1. And by iterating this scheme, we get that Pn equals P to power n. So this means that the nth power of matrix P describes the probability of going from a state to another in exactly n steps. And this is a deep insight into the long-term behavior of a probabilistic model. Here is another example, a protein with two phosphorylation sites. And each site can be either phosphorylated or not. And so overall our protein can have 0, 1 or 2 of its sites phosphorylated. And we want to follow the events in the system. So in this model we will have that from being 0 phosphorylated, there is a 100% chance that at some point we will become 1 phosphorylated. And once you are having one of the sites phosphorylated, there is a 45% chance that the other site will also be phosphorylated, meaning that we transition to state 2 where we have two sites phosphorylated. But there is also a chance of 55% that in fact the phosphorylated site will get unphosphorylated, so meaning that we go from state 1 to state 0. And finally, when we have both sites phosphorylated, there is a 100% chance that the next event in the system is going to be one of unphosphorylation, moving us to state 1. The same thing can also be collected as we did before in terms of this transition probability matrix P. And so if you start with a 0 phosphorylated protein, we can now look into what would be the prediction for the next few steps. And to do that, we simply start with the initial state being 1, 0, 0, meaning that we have a 0 phosphorylated protein, and we simply have to compute the product x0 times p to power n. The model is a little bit different if we think separately about the phosphorylation status of two sites, meaning that we no longer say that we have up to 2 phosphorylation sites, but we want to say which one of them is phosphorylated. So in this case, our model will have 4 states. The first one is unphosphorylated, as is the second one. The state where the first one is unphosphorylated but the second one is phosphorylated. The state where the first one is phosphorylated and the second one unphosphorylated, and finally the state where both are phosphorylated. And the same thing can now be seen in a graphical way as we have done before. It's just that now having 4 states, the plot is going to look somewhat more complicated and we have more edges and more probabilities to describe between these 4 states. And these probabilities can also be written down as we have done before in terms of a probability transition matrix. And because we have 4 states, this matrix will have dimensions 4 by 4. Here is an example of a different type. We will say that a device, let's say a computer or a network, is reliable if it performs well for a reasonably long time. And so the reliability of a device really is the probability that it will not fail over a specific time period. If we have a series systems, meaning a sequence of devices, they will function even only if all of its devices are functioning. And so let's say that the reliability of the first device in this sequence is 0.9. And after it we have a device with reliability at 0.95, and finally the third one has reliability 0.96. And so the system's reliability, because all of them have to be functioning, is really the multiplication of the reliability of each one of them, so meaning that R of t is R1 times R2 times R3, and that's 0.82, which is, as you might expect, less than each component's reliability. A similar example now about parallel systems. Parallel systems function well as long as at least one of their components function well. In other words, it fails if and only if all of its devices fail. To calculate the reliability of such a system, R of t, in fact it's easier to think about its fail probability, and the fail probability is 1 minus R of t equals, and because this is a parallel system, it fails if and only if all of its devices fail. So in our case it's going to be the probability of failing, the first one, so it's 1 minus R1 of t, times the probability that the second one fails, so it's 1 minus R2 of t. And that in our case can be calculated to be 0.998. And that is, as you might expect, higher than any of the components' reliability.